Hello everyone, my name is Rahul Arunachalam Murugan. I am here to present my project on piston effect mitigation in a Hyperloop system. Hyperloop is a high-speed transportation system. This concept was first proposed by Elon Musk in 2013. This concept aims to provide a rapid and an eco-friendly transit alternative. This concept encounters lots of challenges. One among them is called the piston effect. This effect is caused due to the pressure accumulation in front end of the aeroshell. Due to this effect, the pressure dissipation through the aeroshell body is uneven, causing the air to choke on the top and bottom region of the aeroshell. The related works for this project are mainly on some topics. They are Hyperloop, piston effect, Kantrowitz's limit, and computational fluid dynamics. The studies provide a technical overview to design a Hyperloop system. The objective of this project is to mitigate the piston effect with the aerodynamic approach. The aerodynamic approach will be by providing a streamlined body, simplified nose cone structure, and the addition of diffusers. The deliverables for this project are 3D CAD model for the aeroshell, parametric contour of pressure, velocity, and streamline, graph plots of drag and lift forces experienced by the aeroshell. The evaluation metrics in this project is to minimize the lift and drag coefficient along with minimizing the lift and drag forces. Upon this, the airflow efficiency is to be maximized through the air shell body. The methodology of this project begins with the sketching of 2D sketches. This sketch is developed into a 3D model using SolidWorks. The 3D model is exported into ANSYS SpaceClaim to design an enclosure domain replicating the Hyperloop's tube. The dimension of the tube can be derived from the equation 1. In SpaceClaim, the body of influence is provided to the 3D model that will be explained in the further slides. Once the enclosure and the body of influence is designed, the 3D model setup is meshed in ANSYS meshing. Once the mesh is generated, the simulation is carried out in ANSYS Fluent and the parametric contours are generated. This chart simplifies the methodology process into three parts: design, analysis, and post-processing. Design includes 2D drawing, 3D modeling, and drafting. Analysis includes enclosure domain, body of influence, mesh generation, and CFD simulation. And finally, the post-processing involves calculation and contour generation. This process will be repeated for different designs and parameters. The anticipated risk that can be encountered during this project is due to the complexity of the model. Since this is a 3D analysis, the mesh generation and the simulation is in large size. As a result, the model consumes a lot of computation power and time, causing the software to crash or damage the hardware of the computer. This risk can be avoided by optimizing the mesh size and by saving the data periodically, leading to fast computation and less power consumption. The preliminary work that has been carried out till now is a 3D symmetric analysis of a basic design of the aeroshell profile. The figure shows the draft of the aeroshell profile. The size of the aeroshell is replicated of the real size model, so the dimensions are in inches. The figure represents the 3D model of the aeroshell. Once the aeroshell is designed in SolidWorks, it is imported into SpaceClaim and the enclosure is designed. The figure on the top right shows the enclosure of the aeroshell. The length of the aeroshell is 100 meters. The figure on the bottom right is the aeroshell's body of influence. The figure next to it is the total setup of the model. The figure shows the mesh generation around the aeroshell's body. This is the model after importing it into ANSYS Fluent for simulations. The simulation is carried out for three different velocities: Mach 1, Mach 2, and Mach 3. In post-processing, the pressure, velocity, and streamline contours are generated. This figure illustrates the pressure contour. We can see the pressure being accumulated in the piston region and experiencing a negative pressure in choked and wake region. The contour in this figure shows the velocity of air passing through the aeroshell. The figure shows the streamlined contour of the air particles flowing through the body of aeroshell. The calculation for the preliminary work is based on the given equations. Equation 1 is to calculate the drag force and equation 2 is to calculate the lift force. D is the drag force and CD is the drag coefficient, which is obtained from the simulation, and L is the lift force and CL is the coefficient of lift. Along with that, A is the cross-sectional area, rho is the density of fluid, that is air in this case, and V is the velocity of the aeroshell. Once the forces are calculated, the graphs are plotted. The graph plot on the left is the coefficient of drag for different velocities, and the graph plot on the right shows the drag force experienced at those velocities. In the same way, the graph on the left is the coefficient of lift at different velocities, and the graph on the right is the lift force experienced at those velocities. The significance of the project is that by overcoming the piston effect, safety and energy efficiency can be enhanced, and seamless operations can be achieved. The intellectual merit of this research lies in advancement of understanding the aerodynamic principles. The broader impact is extended to the transportation industries, influencing urban mobility and global effort towards environmentally conscious transit technologies. Thank you. If any questions, please do reach out to rahul.arnachalamvelmurugan@sjsu.edu.